GCE Advanced Level Chemistry Practical Series Experiment number 39. Experimental determination of the relative positions of commonly available metals in the electrochemical series. The aim of this experiment is to observe displacement reactions among metals and metal ions, to arrange the metals in a series based on their reactivity, and to determine the relative positions of metals in the electrochemical series. So students, after identifying these aims, we can now move on to identifying the chemicals and equipment we will be using for this experiment. Students, let's identify the chemicals and the equipment we will be using for this experiment. We'll be using sodium sulfate, magnesium sulfate, lead nitrate, copper sulfate, ferrous sulfate, and finally zinc sulfate. And we'll be using these solids and we'll be dissolving them in water to prepare 1 moles per decimeter cube concentrated aqueous solutions. In order to prepare those solutions, we'll be using a measuring cylinder to measure 50 milliliters of distilled water, and we'll be measuring the relevant masses we need, and we'll be preparing 1 moles per decimeter cube concentrated solutions into each of these beakers. And even the beakers are labeled so that we can identify which solutions are in which beaker. Apart from those chemicals and the equipments I just mentioned, we will be using the metals that we have here as well. We'll be observing how different metals are capable of displacing different metal ions. So we will be needing pieces of metals in this reaction. So we have 5 different metals here. So we have copper. You can observe the color of copper. And then we have lead. We have small cut pieces of lead here. And we have magnesium. So keep in mind, students, before you use magnesium, to clean the magnesium strip, otherwise there will be outer coating that might interfere with our reaction. We have iron. Small cut pieces of iron are here. And then finally we have zinc. So we will be using these metals in this experiment, and we are going to observe how these metals are going to displace some of the metal ions found in the solutions we prepare in the beginning of this experiment. Apart from these metals, we'll be using other equipment like spatula. We'll be using watch glasses, and we will be using test tubes. Now keep in mind, students, each of these test tubes will be labeled. The label would read what 2 components are mixed in the test tube. Over here it reads lead and zinc 2+ ions. So we are going to observe in this test tube what happens when lead metal is added to a solution containing zinc 2+ ions. So in other words, to a portion of zinc sulfate solution, we are going to add a lead metal piece and observe whether there's going to be any displacement reaction. Then we have a digital balance over here that we'll be using to measure the right masses of these solids when it comes to preparing 1 moles per decimeter cube concentrated solutions of each of these compounds. So now, students, we have identified the chemicals. We can move on to our experiment. But Before we move on to our experiment, let's try and understand what is actually going to happen in this experiment, or experiment number 39. So we are trying our best to identify in which regions of the electrochemical series each of these metals are going to appear. If you take a look at the electrochemical series has elements arranged based on their reduction potential. Now students, the more negative the reduction potential of an element is, that element is more likely to get oxidized. Or we say, if you take a look at the electrochemical series, you have the reactions written down. It's a reversible reaction, and you can see when it comes to each element, the reversible reaction is written, and right next to it we have the reduction potential written. If the reduction potential is a large negative value, that would indicate the equilibrium position of the given equilibrium lies more towards the left hand side, meaning if the reduction potential is quite negative, those elements prefer to be oxidized than being reduced. So if you take elements like magnesium, the reduction potential is a large negative value. It is minus 2.36 for magnesium. This indicates that magnesium's equilibrium position when it comes to the reduction equation lies more towards the left hand side, indicating magnesium is going to be more oxidized than being present in the reduced form. In other words, we could state that magnesium donates electrons or releases electrons more readily. So therefore, magnesium acts as a reducing agent. If you take a look at copper reduction potential is going to be plus 0.36. This is a positive value. So the positive values would indicate, or smaller negative values would indicate, that the equilibrium position of the written equation or written equilibrium reaction is going to be lying further to the right hand side, or that means those kind of substances prefer to be reduced more than oxidized. So we can also state, when it comes to copper compared to magnesium, copper accepts electrons readily. Therefore, copper 2 plus ions are the ones who can accept electrons readily. So copper 2 plus ions act as oxidizing agents. So based on the reactivity of the elements that we see in the electrochemical series, we can prepare our activity series, or activity series sometimes is also known as the reactivity series. Reactivity series includes metals arranged according to their reactivity. Most reactive metals are going to be found on the top of the reactivity series, and as we go down, the reactivity of the metals found in the reactivity series is going to decrease. So the least reactive metals are going to be found at the lower end or bottom end of the reactivity series, and the elements that are found on top of the reactivity series are going to be more reactive elements like potassium, magnesium, calcium, and so on. And elements that are found towards the bottom of the reactivity series, elements like copper, are going to be less reactive. And as you know, students, through experience, elements like sodium, potassium usually reacts even with cold water. And as we go down, elements like magnesium wouldn't react with cold water, but with steam or hot water, it will start to show a small reaction. With steam, it will react readily. However, as we go down further down the reactivity series, when you encounter elements like copper, we know elements like copper do not react with water. We also know, unlike all the other metals, copper do not react with acids as well, right? So this indicates that copper is going to be less reactive. So students, we are going to observe in this reaction how different elements or different metals that we have over here react with different solutions that we have over here. More reactive metals are capable of displacing metal ions of less reactive metals. So when we add each of these metals into these solutions containing different metal ions, if the metal ions that are present over here are going to be less reactive than the metals that are introduced into these solutions, we can observe a reaction happening. For example, if you add a magnesium piece to a solution containing copper 2 plus ions, we just stated that magnesium is higher in reactivity than copper. So magnesium metal, when introduced into a copper 2 plus ion solution, you will observe that copper 2 plus is going to get displaced as copper solid. So you would observe the formation of a brown color precipitate. So throughout this experiment, we are going to observe how different metals are capable of displacing different other metal ions with lower reactivity. If the reactivity of the metal ion solution or metal ions that we have over here is greater than the metal that we introduced, there will not be any reaction. So students, while keeping this on mind, we can now move on to the first step of our experiment. In the first step of our experiment, we will be preparing the solutions needed for this experiment. So we are going to measure the right masses of each of these solids, and we are going to prepare 50 milliliters of each of these solutions. So let's move on to that part of our experiment. Now students, let's prepare our first solution. We have a beaker labeled zinc sulfate, and we have our digital balance turned on, and we are going to place this beaker on the digital balance, and it reads 50.97, but we do not need this measurement as we are going to tear the digital balance and get the digital balance to read 0. Afterwards, we will take our zinc sulfate solid. So what we have over here is our zinc sulfate solid, and we will measure 8.07 grams of zinc sulfate over into our beaker here. We will measure exactly 8.07 grams. You can see zinc sulfate is a white color solid. We have measured exactly 8.07 grams by now. After measuring exactly 8.07 grams, we will remove our zinc sulfate solid, and we are going to add exactly 50 milliliters of water. Usually students, when you are preparing a solution to a higher level of accuracy in concentration, we would normally use a volumetric flask, and we will add the weighed mass into the volumetric flask by dissolving it in water with the use of a wash bottle, and then we will bring the entire volume of the solution up to the calibration mark in the volumetric flask. However, students, in this particular experiment, we are trying to prepare a solution of zinc sulfate and all the other sulfates and nitrates in the experiment, roughly to a concentration of 1 moles per decimeters cube. Since this is not a reaction where we are going to titrate these solutions against anything else, we are not going to be preparing these solutions with the use of a volumetric flask. We are going to need solutions with a concentration of roughly 1 moles per decimeters cube. So therefore, we will not be using a volumetric flask here. So after measuring zinc sulfate solid over here, we can keep it aside. We will add 50 milliliters of water to each of these solutions later on. We measured the mass of zinc sulfate first. We'll leave it aside, and then we can move on to ferrous sulfate. And we have a beaker labeled ferrous sulfate. So we will first of all place the beaker on our digital balance, and then we will tear the digital balance. Then we will take exactly 7.6 grams of ferrous sulfate. That is the mass of ferrous sulfate needed to prepare roughly 1 moles per decimeters cube concentrated ferrous sulfate solution. We are trying to prepare 50 milliliters of ferrous sulfate solution with that concentration. So we need to measure exactly 7.6 grams. You can observe that ferrous sulfate crystals here are a light greenish blue in color. We need 7.6, we need a little bit more. We have measured 7.61 of ferrous sulfate. Now, before adding water, we will leave it aside. So keep in mind, we are going to measure the relevant masses of each of these solids first, and then after we have measured all of the masses, we will add 50 milliliters of water to each of these beakers we have over here, and then we'll prepare the solutions. And then, students, we move on to copper sulfate. So we have a beaker labeled copper sulfate, right? So, and we are going to measure the right amount of copper sulfate over here. So as you know, copper sulfate comes in two main forms, the anhydrous form and the hydrated form. So what we actually have over here in this container is the hydrated form. So hydrated form of copper sulfate, students, you should remember, appear blue in color. The anhydrous form of copper sulfate would appear white in color. So after placing our beaker, we will tare the digital balance to get to a 0 reading, and then we will measure 16.9. So what we have over here is copper sulfate 10H2O. So we are going to measure 16.9 grams of copper sulfate. We have measured 16.91 grams of copper sulfate. After measuring the relevant mass, we will keep the beaker aside. And as I mentioned earlier, we will be adding water to each of these solutions later on. And then we will take lead nitrate. We will tare the beaker first, or tare the digital balance first. And then we have our lead nitrate container, and we are going to measure exactly 16.56 grams of lead nitrate to prepare 1 moles per decimeters cube solution of lead nitrate with a volume of 50 milliliters. So let's measure 15 or 16.59 grams of lead nitrate. Now, students, we have measured exactly 16.60 grams of lead nitrate, and you can actually make an interesting observation here. That is, lead is a heavier metal. So therefore, when you are talking about lead nitrate, the lead nitrate mass that we need to measure to prepare 1 moles per decimeters cube concentrated lead nitrate solution was greater than the masses that we had to measure for zinc and iron and copper. Mass of copper sulfate we measured also came up to 16.9 grams because it was attached to 10 water molecules. However, the mass of lead nitrate alone that we have to measure to prepare 1 moles per decimeters cube concentrated solution is much greater than all the other salts because lead is a heavier salt. And another observation you can make is the fact that 16.6 grams of lead nitrate is only going to fill up our beaker. Only the bottom is barely covered. But when it comes to talking about 16.9 grams of copper sulfate, you can observe how much more copper sulfate we had to take to reach a similar mass, right? Over here, when it comes to copper sulfate we measured 16.9 grams, and over here when it comes to lead we measured 16.6 grams. Only 0.3 of a gram difference is there. However, you can see the difference in the amount of solid we have taken. So copper is a lighter metal than lead, so that is why when it comes to lead nitrate, a smaller uh, amount of substance is going to have a greater mass. So now students, after making that observation, we can move back into measuring magnesium sulfate. So we have magnesium sulfate labeled beaker here, and then we will tear the beaker. After tearing the beaker, we can measure magnesium sulfate needed for our experiment. We need 6.02 grams of magnesium sulfate. So we will measure 6.02 grams. Now students, we have measured the right mass of magnesium sulfate we needed to prepare 1 moles per decimeter cube concentrated magnesium sulfate solution. And then we finally move on to sodium sulfate. So we have a beaker labeled sodium sulfate, so we are going to measure the right mass of sodium sulfate into this beaker. We'll place the beaker on the balance, and then we will tear the balance. Afterwards, we can measure exactly 7.1 grams of sodium sulfate. We have measured 7.11 grams of sodium sulfate. This mass will be sufficient to prepare the solution that we need to prepare. So now students, we have measured the masses of these salts that we need to prepare 1 moles per decimeter cube concentrated solutions of each of these salts. And now it is time for us to add the relevant volume of water. So these mass measurements were taken to prepare 50 milliliters of the solution. So we need to measure 50 milliliters of water, and then we need to add that water into each of these beakers. So let's proceed to do that. So we have our zinc sulfate over here, and we have a beaker filled with distilled water, and we have a measuring cylinder that could read up to 50 milliliters. So we are going to add 50 milliliters of water. After adding 50 milliliters of water into the measuring cylinder, students, you can bring the measuring cylinder to your eye level, or you can bring your eye level to the level of 50 milliliter mark on the measuring cylinder, and ensure that the volume that you have measured is correct. Now after reading the volume correctly, you can then proceed to add this 50 milliliters of water into each of these beakers. And then you can take a clean stirrer and mix the contents in the beaker until all of the solid completely dissolves. Now students, this is how we are going to prepare all of these other solutions as well. So since this is a repetitive process, we will be preparing the rest of the solutions off camera. And students, after preparing the solutions like this, you can see we have dissolved all the solid and prepared our zinc sulfate solution. After preparing each of these solutions like this, we will take those solutions and we'll bring it to the next part of our experiment. Now students, we are going to observe how the metal copper reacts with each of these metal ion solutions. So we have 6 different solutions here: zinc sulfate, ferrous sulfate, copper sulfate, lead nitrate, magnesium sulfate, and sodium sulfate. Now each of these solutions contain different metal ions. Zinc sulfate contains zinc 2 plus metal ion, ferrous sulfate contains Fe2 plus metal ion, copper sulfate contains Cu2 plus metal ion, lead nitrate Pb2 plus or lead 2 plus metal ion, magnesium sulfate contains magnesium 2 plus metal ion, and finally sodium sulfate contains sodium 1 plus metal ions. Now students, what we are going to do is we are going to add the metal copper that we have over here. We have cut pieces of copper metal. So we are going to add cut pieces of this copper metal into each of these solutions, and we are going to observe if copper metal is reactive enough to displace the other metal ions that are present in the aqueous mediums that we have over here. So in order to do that, we are going to first of all withdraw around 5 milliliters of each of these solutions into these test tubes. These test tubes are labeled ranging from zinc 2 plus ion solutions to all the way to our sodium 1 plus ion solutions over here, right? So they are properly labeled. So first of all, we are going to take 5 milliliters of these solutions into each of these test tubes. So to the test tube labeled zinc 2 plus ions, we are going to take around 5 milliliters of zinc sulfate solution. And then to the test tube labeled Fe2 plus ions, we will take our ferrous sulfate solution. Ferrous sulfate, students, as soon as you prepare the solution, it will appear a pale green color or blue-green color. But as you allow it to stand in air, it will get oxidized to form Fe3 plus ions gradually. So the solution might change its color a little bit. So keep that in mind. If you need to have a fresh solution each time you do this experiment, then you can prepare a fresh Fe2 plus solution and then proceed with the experiment. So still the solution can be used. It has a green hue. So we will be taking roughly around 5 milliliters of the solution into our second test tube. And then to obtain copper 2 plus ions, we use our copper sulfate solution. As you can observe, copper sulfate solution is a blue color. And to the test tube labeled copper 2 plus ions, we are going to add around 5 milliliters of copper sulfate solution into the test tube labeled Cu2 plus ions. And there's another test tube labeled Pb2 plus and copper. So to that, we will be adding our lead nitrate solution. And there's another test tube labeled Mg2 plus ions added with copper metal. So that means into that test tube we need to take Mg2 plus ion solution, which is obtained from magnesium sulfate. And finally, we have a solution of sodium sulfate here. So we will add sodium sulfate solution into our last test tube labeled sodium sulfate or sodium 2 plus ions. Now we have taken into each of these test tubes these 6 different solutions we have prepared in the previous part of our experiment. So now all that is left for us to do is add the copper metal into these solutions to observe whether copper metal is reactive enough to displace any of the metal ions present in these aqueous solutions. So we have copper metal here. We have small cut pieces of copper metal. We'll take a few pieces of copper metal and add to each of these test tubes. Now students, as you can see, we have added pieces of copper metal to each of these test tubes. To get them to come into contact with the solution better, we can shake the test tubes a little bit, because some of the copper pieces are floating on the surface. So to get them to be submerged in the solution, we can shake the test tubes a little bit. Now we will wait for about 5 to 10 minutes and observe whether there is a reaction between the copper metal and each of these solutions that we have over here. If there is a reaction, you will observe a color change in the medium, or you will observe the formation of some sort of precipitate. So we will come back in 5 to 10 minutes and observe if there has been a reaction in each of these solutions. Students, it has been 10 minutes and we can observe no color change or no formation of any precipitate in any of these test tubes. But let's closely observe. You can see when it comes to the zinc 2 plus ions and copper metal, there is no reaction between the two. And when it comes to Fe2 plus ions or ferrous ions and copper metal, you can see that there is no precipitate or any other color change observed here. When it comes to copper 2 plus ions mixed with copper metal, you can see no precipitate, just the copper pieces at the bottom of the test tube. There is no precipitate or anything, any other observation that you can see over here. When it comes to copper and lead 2 plus ion solution, you do not observe a precipitate being formed, just the copper metal pieces at the bottom of the test tube is there. No color change has taken place as well. When it comes to magnesium 2 plus ion solution and copper, there has been no reaction here as well. And sodium 1 plus ions and copper, we do not observe any reaction here as well. Now students, what does this communicate to us? So we can conclude after observing these observations that copper metal was not reactive enough compared to all of these metal ions or metals. Copper metal was not reactive enough to displace any of these metal ions as they are metal. So out of these metals that we have over here, copper is supposedly the least reactive metal that we have here, because it was not able to displace at least one metal ion into its metal, indicating when you compare zinc, ferrous, copper, indicating when you compare the metals that are present here in the ion form, sodium, magnesium, zinc, ferrous and lead, all of these metals were more reactive than copper, right? So all of the elements or the metals that we have over here are more reactive than copper. Copper is the least reactive metal out of the metals that we have here in our experiment. So After making note of that, we can move on to the next metal, lead. Now students, we move on to observe how lead metal reacts with zinc sulfate, ferrous sulfate, copper sulfate, lead nitrate, magnesium sulfate, and sodium sulfate. So we'll first take around 5 milliliters of these solutions into each of these test tubes. Now these test tubes are labeled accordingly. So the test tube over here has the label Zn2 plus, indicating that we'll be taking zinc sulfate solution into this, because zinc sulfate solution will have zinc 2 plus ions in it. And then we have Fe2 plus, Cu2 plus, Pb2 plus, Mg2 plus, and sodium 1 plus, or Na1 plus. Into each of these test tubes, we will now take the relevant solution. So for the first test tube, we will take around 5 milliliters of zinc sulfate solution. You can see to the zinc 2 plus labeled test tube, we have taken zinc sulfate solution, and we will repeat the process with other test tubes as well. To the test tube labeled Fe2 plus, we added the ferrous sulfate. To the test tube labeled Cu2 plus, we are going to add copper sulfate solution. And to the test tube labeled Pb2 plus, we will add Pb nitrate or lead nitrate solution. And to the test tube labeled Mg2 plus or B5, we are adding magnesium sulfate solution. And finally, to the test tube labeled Na1 plus or B6, we are adding sodium sulfate solution. We are introducing sodium 1 plus ions into the medium. We are adding this solution into this test tube so that this test tube contains a solution with sodium 1 plus ions. Now students, after we have taken each of the different solutions into these different test tubes, it is time for us to add lead metal into each of these test tubes. So let's take a small piece or a small amount of lead metal into each of these test tubes. As you can see, lead metal sinks easily to the bottom of each test tube. Unlike copper, we observed copper did not easily sink to the bottom of the test tube when we added copper metal into each of these test tubes in the previous experiment. And copper was made into thin sheets and we have cut it into small pieces. However, since metal copper was somewhat lighter, we observed the fact that it was floating on the surface of the water due to surface tension of water. However, when you mixed it, due to the weight of copper, it sank to the bottom of the test tube. However, when it comes to lead, you don't observe that. Lead easily sinks to the bottom because lead is a heavier metal than copper. So it will not be remaining on the surface of the aqueous layer. Instead, it will directly sink to the bottom. One of the very small observations you can make, and you can develop an idea about how the densities of different metals vary when you are carrying out an experiment like this. Copper is a lighter metal than lead. Now students, after adding the lead metal pieces into each of these test tubes, we can shake these test tubes a little bit. and then we can allow the reaction to take place for about 10 to 15 minutes in this case, because lead will not react very fast with any of these solutions. So you will have to allow the reaction to take place for a little while longer than recommended. So at that point you will see lead metal will react with certain aqueous solutions that we have over here. So what we are trying to observe is which metal ions will get displaced in the presence of lead. So we will allow this reaction to happen for a while, and then we will come back and observe which metal ions have been displaced as solid metal in the presence of lead. Now students, let's observe what has happened to our solutions after we allowed the reaction to take place for about 10 to 15 minutes. So you can see over here all of the solutions except for one solution has not shown any reaction. So let's first take a look at the solutions that has not shown us any reactions. So if you take a look at when lead was added to zinc 2 plus, we don't observe any color change and we don't observe a precipitate formed as well. So this indicates the fact that zinc 2 plus ions were not displaced by lead solid, or zinc 2 plus ions were not displaced by lead metal. We can say the same about Fe2 plus ion solution as well. We observe over here there is no precipitate formed, only the lead pieces at the bottom are present. You can barely see the lead piece. However, the lead piece is still there in the test tube, and there has not been any color change as well. Again, this indicates that the lead metal was not capable of displacing our Fe2 plus ions into iron or iron metal. Then we will move on. We'll talk about the copper sulfur solution later. Then we'll move on to the other solutions that did not show reaction. If you take a look at lead metal reacting with lead 2 plus ions, since the lead metal is present in its own ions, there is not going to be any reaction here, and you will see there's no color change, as well as the lead metal pieces we added into this solution is still at the bottom unreacted. And then we have a lead metal added to magnesium 2 plus ion solution. No color change here and no precipitate is observed. This indicates that the lead metal did not react with magnesium 2 plus aqueous solution. So we can conclude that in this situation also, lead does not react or displace magnesium 2 plus ions into magnesium solid. And finally, we have sodium 1 plus ion solution, and we can see over here there is no reaction observed as well. So in this experiment we are going to observe if there has been any reaction or if there's going to be any color change or a precipitate observed. So in this case, no new precipitate is observed, only the magnesium pieces we added to the solution is present at the bottom of the test tube, and there's no color change as well, indicating that sodium 1 plus ion solution did not react with lead metal. However, students, if you take a look at this copper 2 plus aqueous ion solution, copper 2 plus aqueous ion solution has very clearly shown a color change. To observe the color change a little bit more clearly, we can take our copper sulfate solution into another test tube. We'll take a little bit of copper sulfate into another test tube, and we can compare this color with the color of the copper sulfate solution that is added with lead metal. So what we have over here is the copper sulfate solution added with lead metal, and what we have over here is copper sulfate that was not added with anything else. So you can very clearly see a color change. The copper sulfate that was added with the lead metal has a brown color precipitate at the bottom. You can observe it when you mix the solution a little bit. You can see that there is a brown color precipitate at the bottom of the copper sulfate solution. So if you want to observe this precipitate a little bit, you can add a little bit of water. You can see as we add water, the copper metal that is present at the bottom as a brown color precipitate gets dispersed a little bit, and you can observe the copper solid particles over here very clearly. Now students, at the bottom of this test tube, the brown color precipitate that you observe is copper. So copper 2 plus ions, they do get displaced as copper solid. So lead metal was capable of displacing copper 2 plus ions as copper solid. So when this is taking place, a lead metal turns into lead 2 plus ions. Lead metal turns into lead 2 plus ions, while copper turns into, or copper 2 plus turns into copper solid. So students, this reaction is what you observed over here. So keep in mind, when the reaction is taking place, copper gets reduced from copper 2 plus to copper metal, and lead metal gets oxidized from lead solid to lead 2 plus, and the copper precipitate will be prominent here. So you will observe the brown color copper solid formed at the bottom of the test tube. So students, what about the color of the copper sulfate solution? Why did the color decrease? Because when it comes to copper sulfate, the blue color in the copper sulfate solution is there because of the complex copper 2 plus ions formed with water ligands. Copper 2 plus ions and water ligands form a complex that is blue in color. So if you have a higher concentration of copper 2 plus ions in the medium, you will observe a very clear blue color. But if you lower the concentration of copper 2 plus aqueous ions in the medium, then you will observe that the color of the solution, the blue color of the solution, will decrease. So in this case, you will observe as copper 2 plus turns into copper solid, the concentration of copper 2 plus ions in the medium will decrease. Therefore, the color of the medium will also change from a very clear blue color to a pale blue color or very light blue color when the copper 2 plus ion concentration drops in the medium. So these are the observations you made in this part of our experiment, and based on these observations, we can conclude that lead was not as reactive as iron, zinc, magnesium, or sodium. Lead was only more reactive than copper. That is why lead was able to displace copper 2 plus ions as copper solid. So lead is more reactive than copper. However, lead is not more reactive than any of the ions that are present over here. So we can conclude lead is not more reactive than sodium. Lead is not more reactive than magnesium, not more reactive than zinc or iron, but lead is more reactive than copper. So after making that observation, we can now move on to the third part of our experiment, where we observe how magnesium react with these solutions. Now students, we move on to the third part of our practical, where we observe how magnesium reacts with the solutions we have over here. So we have the magnesium metal pieces here. Keep in mind, whenever you take magnesium metal, you have to make sure that the outer coating of the magnesium strip is cleaned. After that, after we observe that the outer coating is cleaned, you will see that the magnesium metal is a shiny metal. Otherwise, if you take a magnesium strip, it is going to look dull and gray in color. But after you remove the outer coating, the magnesium metal should look shiny like this. So after cleaning the magnesium metal, we will cut it into pieces. and we have obtained our magnesium metal pieces here. And like we did in the previous uh, parts of the test, we will take each of these solutions and we will transfer around 5 milliliters of these solutions into each of these test tubes. So let's go ahead and do that. There's a test tube labeled zinc 2 plus. To that we will add our zinc sulfate solution. There's another solution here, ferrous sulfate. Now we have a test tube labeled Fe2 plus, and this is a freshly prepared ferrous sulfate that we have over here. So you can observe the color of the ferrous sulfate, a pale greenish color. And after transferring about 5 milliliters of ferrous sulfate into a test tube labeled Fe2 plus, we can now move on to copper sulfate. We have copper sulfate here, and we will transfer around 5 milliliters of copper sulfate into the third test tube labeled copper 2 plus ions, and then we will move on to lead nitrate. We have a test tube, or we can say C4 test tube labeled Pb2 plus. So we are adding lead nitrate solution into that test tube. C5 test tube has magnesium 2 plus ions written in the label, so we will transfer magnesium sulfate into our C5 test tube. And finally, to our sodium 1 plus labeled test tube, or C6 test tube, we are going to add sodium sulfate. Now students, we are going to be adding magnesium metal pieces into each of these solutions we have over here. Now keep in mind, as soon as you add magnesium, you will see a reaction happening, as magnesium reacts slowly with water as well. So you will see a reaction taking place, but keep in mind that will not denote whether magnesium is displacing the metal ion in the medium or not. So we will get on to the details about it after adding the magnesium pieces into each of these test tubes. So we are adding small amount of magnesium into our zinc sulfate solution, a few pieces of magnesium into our iron sulfate or ferrous sulfate solution, and then we have copper sulfate solution here. We have lead sulfate solution, magnesium 2 plus solution, and then sodium 1 plus ion solution. Now students, after adding magnesium into each of these solutions, you can see, if you observe over here, with zinc 2 plus aqueous ion solutions, as well as in sodium 1 plus aqueous ion solution, we observe that there is a small amount of bubbling that is taking place. I have only added a very small piece of magnesium into our sodium 1 plus aqueous ion solution. We'll add a little bit more. So you can observe, even in sodium 1 plus aqueous ion solution, magnesium shows a reaction. Now this reaction, the bubbling that you observe over here, is due to magnesium reacting with the water in the medium to produce hydrogen gas. So magnesium could react with water and produce hydrogen gas. As you know, magnesium is present in the second group of the periodic table. It's an alkali earth metal, and this group shows very slow reaction with cold water as well, but with hot water or with steam, you will show it will show faster reactions. So the bubbling that you observe is due to magnesium mainly reacting with water. But if you allow this reaction to take place for a while, now you can observe already when it comes to copper 2 plus solution, the solution has started to react with magnesium 2 plus ions. The color of the solution also has started to change, and we can see a precipitate getting collected at the bottom as well. So there are certain solutions already starting to show very clear reaction between magnesium and the solution ions or metal ions in the solution. But when it comes to few other solutions, for example, if you take magnesium 2 plus ions added with magnesium, you would not see a reaction other than hydrogen being formed when magnesium reacts with water, because magnesium cannot react with magnesium 2 plus ions and displace them. So you don't see a reaction here. But in all the other test tubes also, whether we have a reaction or not cannot be determined just by the bubbling that you observe in the test tube. A gas being produced when we add magnesium piece into water just indicates the fact that magnesium is reacting with water to form hydrogen gas and magnesium hydroxide. So students, over here, if you allow these reactions to take place for a while, you will observe a small color change in certain solutions as well as certain precipitates being formed. So for those types of reactions to happen, we will allow this reaction to take place for about 10 to 15 minutes. And after the reaction has taken place, and when we have a very clear observation, we'll come back and talk about the observations. Now students, let's observe out of the solutions that we took into different test tubes here earlier, which solutions have shown a reaction with magnesium. Now we know magnesium is in the group 2 and it's a very reactive element compared to most other elements that you find. And if you remember the electrochemical series, magnesium is present higher up on the electrochemical series. Out of the solutions that are over here, you can observe the zinc solution shows a clear reaction here. You can see when you shake it, a whitish precipitate is observed. So zinc 2 plus ions have been displaced as zinc solid. So that indicates magnesium has reacted with zinc 2 plus ion solution and has displaced zinc 2 plus ions as zinc solid, and magnesium has turned into magnesium 2 plus ions. So we can conclude magnesium is more reactive than zinc, or in the reactivity series, we can conclude magnesium is found above zinc. Now we can move on to Fe2 plus aqueous ion solution. We can observe here Fe2 plus has shown a color change, and we can see a precipitate being formed as well. So this indicates magnesium has reacted with ferrous ions as well. At the bottom of the test tube, we can see small black color particles, but those are extremely small students. You might not be able to observe them in the camera. However, magnesium has displaced Fe2 plus or ferrous ions as iron or iron metal. So students, this indicates that magnesium is more reactive than iron. That is why ferrous ions were displaced as iron solid. So in the reactivity series, magnesium is found above iron. So we found out magnesium is more reactive than zinc and iron at this point. What about copper? Copper is not a very reactive element. So magnesium is a very reactive element, and you can very clearly see that copper has reacted with magnesium. Copper 2 plus ions in the medium, they have gotten displaced as copper solid. We can see at the bottom of this test tube a brown color precipitate. This indicates that copper has gotten displaced as copper solid or copper metal. When you disperse the copper solid, we can observe the solid particles over here. If you want to very clearly observe that, we can dilute this a bit further. And the copper metal that is formed, tiny particles of copper metal is dispersed in the aqueous medium over here, and majority of the copper metal is at the bottom of the test tube. So you can observe this brown color precipitate very clearly after diluting the solution. So the copper 2 plus ions in the medium has gotten displaced by magnesium. Magnesium will get oxidized to form magnesium 2 plus, while copper 2 plus ion will get reduced to form copper solid or copper metal. Now students, we move on to the fourth test tube here. So in this fourth test tube, we had lead 2 plus ions. What do you observe? Has a reaction happened? By the looks of it, yes, a reaction has taken place. We can see that at the bottom of this test tube, a whole blob of lead has been formed, and tiny particles of lead metal is dispersed in the aqueous medium here. So we have over here lead 2 plus ions in this medium, and these lead 2 plus ions were displaced by the magnesium metal that we added. At the bottom of the test tube, we can observe a slight gray color precipitate. This is the displaced lead metal. Pb2 plus aqueous ions got displaced as Pb solid, or lead 2 plus got displaced as lead solid, while magnesium metal or magnesium solid got oxidized into magnesium 2 plus aqueous ions. So in the electrochemical series as well as in the reactivity series, magnesium is found above lead, meaning magnesium is more reactive than all four of these metals. Magnesium is more reactive than zinc, magnesium is more reactive than iron, magnesium is more reactive than copper, and magnesium is more reactive than lead as well. But when magnesium was added to magnesium 2 plus aqueous ion solution, will there be a reaction happening? Can magnesium displace its own ions? That won't necessarily happen. There is an equilibrium between magnesium and magnesium 2 plus ions. However, there won't be a displacement reaction that is going to be observed like we observed in the previous instances. What about sodium 1 plus ions? Did sodium 1 plus ions get displaced by magnesium? Do we see a precipitate being formed here at the bottom of this test tube? The observation would be there is no reaction when it comes to magnesium with sodium 1 plus aqueous ion solution. This is because, students, magnesium is less reactive than sodium. Magnesium is not going to be able to displace sodium. The only reaction that you see over here is effervescence or bubbling around the magnesium strips that we added. This is because, students, when magnesium is added to water, it will react with water, even cold water. It will react slowly with cold water and will produce magnesium hydroxide and hydrogen gas. So that's the reaction that you observe over here, students. Other than that, there is no other reaction that is taking place here. So after this third part of our experiment, we can conclude magnesium reacted with the most amount of metal ions that we found over here. Magnesium reacted with 4 solutions out of the 6 solutions we have over here, indicating magnesium was more reactive than all of those metals that are present here. So what are the metals that magnesium was more reactive than? Magnesium was more reactive than zinc, iron, copper, and lead. Out of the metal ion solutions that we have over here, magnesium was more reactive than zinc, iron, copper, and lead. However, sodium was more reactive than magnesium. That is why we didn't observe reaction with magnesium and sodium 1 plus ion solution. After making note of that, we can now move on to the fourth part of our experiment. Now, students, we are going to observe how iron reacts with the solutions we have here. So, like we did in the previous parts of this experiment, we are going to take around 5 milliliters of the solutions we have here into each of these test tubes, and these test tubes are labeled accordingly. So let's take our zinc sulfate solution, and we will transfer around 5 milliliters of zinc sulfate solution into the test tube labeled Zn2 plus, or in this case D1. Take a look at the tube labeling, D1 tube, and it is labeled Z2 plus, Zn2 plus, and Fe. So this means we are going to add iron into zinc 2 plus aqueous ion solution. And then we have ferrous sulfate. We'll transfer 5 millimeters of ferrous sulfate into our test tube over here, or D2 test tube labeled Fe2 plus. We have copper sulfate. We'll take our copper sulfate solution and we'll add around 5 milliliters of copper sulfate into a test tube labeled B3 or Cu2 plus. And then we have lead nitrate. We will add 5 milliliters of lead nitrate or lead 2 plus aqueous solution into the test tube D4 labeled Pb2 plus, and to the D5 test tube we are going to add around 5 milliliters of magnesium 2 plus aqueous solution, and to our D6 test tube we are going to add sodium 2 plus aqueous ion solution. So we have taken roughly around 5 milliliters of the solutions into these test tubes. Now we are going to add our iron metal pieces into each of these test tubes. So let's add a few pieces of metal iron into each of these test tubes. Now students, we have added metal iron or iron solid into each of these test tubes. We can mix it well after adding the metal into each of these solutions, and we will mix and allow the reaction to take place for around 10 to 15 minutes. So we will shake each solution like so, and then we will allow it to settle for a duration of around 10 to 15 minutes as I mentioned earlier. So I will continue to mix each of the solutions like this, and you can see you don't observe a reaction straight away. Iron will not react readily like magnesium does with water. Iron will, however, be able to displace some of the metal ions as they are metal, especially if iron is more reactive than the metal ion present in the medium. Finally, we have sodium aqueous solution added with a piece of metal iron or iron metal, and we have mixed all of these solutions, and each of these solutions contain a small amount of iron solid in the medium. So we will allow the reaction to take place. It will take about 10-15 minutes. In the lab when you're conducting this, if you do not observe any noticeable observation, that means you need to allow the reaction to take place for a little while longer. At that point, you will be able to observe some sort of a color change or a formation of a precipitate. So students, We will now allow this to react for a period of time, and after we have observed noticeable observation, we will come back and then talk about the observations we have here. Students, now we join you after we allowed all of these solutions to react with the iron metal piece that we added into each of these solutions. So now let's observe which solutions actually have reacted with the iron metal piece that we added into the solution. So let's take our zinc 2 plus solution. We do not observe any color change or formation of any precipitate over here. The added metal piece is still at the bottom of the test tube without any reaction. So this indicates, students, that there has not been a reaction between Fe solid and zinc 2 plus aqueous ions. What does this indicate? This indicates that iron is not more reactive than zinc, or in other words, zinc is more reactive than iron. So in the reactivity series or activity series of metals, zinc ranks higher than iron. Zinc is found higher in a higher position than iron. Then we move on to Fe2 plus aqueous ion solution or ferrous ion solution. You can see ferrous ion solution has not undergone any change. At the bottom of the solution, you can still find the metal piece that we added. There has not been any change, no color change, or we don't see any precipitate being formed here as well. So this indicates Fe2 plus and metal ion has not shown any reaction. Of course, students, metal solid cannot displace Fe2 plus ions, right? It's a part of the same equilibrium, so it cannot displace Fe2 plus ions. So because of that, students, we don't see a reaction here. Then we move on to copper. Over here, we have the copper 2 plus aqueous ion solution. At the bottom, you can see a brownish precipitate. So this indicates that copper 2 plus aqueous ions have reacted with the solid iron that we added into this medium. So this is a very interesting precipitate. You can very clearly see the precipitate, and the color of the copper sulfate in the medium has gone down. Let's take a closer look at the precipitate. Now students, if you mix this precipitate, you can see this is a brown color precipitate. Now students, when you mix it, you can very clearly see the brown color precipitate. So the brown color precipitate that we see over here is copper solid. The copper 2 plus aqueous ions that were present in the medium were reduced to form copper solid, while the iron that we added to the medium oxidized to form Fe2 plus. So what we have over here is a displacement reaction taking place in the presence of solid iron. So as iron gets oxidized, the copper gets reduced to form copper solid. And if you take a look at the color difference between the solutions, if you take a small copper sulfate solution into a different test tube over here, you can very clearly see the color difference. The copper sulfate solution is a very clear blue color, but when it comes to the copper sulfate solution added with our iron solid, you can observe the color of the solution that has reacted with iron has decreased substantially, because majority of the copper 2 plus aqueous ions that were in the medium has now turned into copper solid. And then we move on to lead 2 plus. So if you take a look at this lead 2 plus aqueous ion solution, you can very clearly observe there has been some sort of a reaction here. You can see a whitish precipitate or grayish precipitate has been formed. So this precipitate is due to lead 2 plus ions getting displaced in the presence of iron. In the presence of iron, lead 2 plus ions get displaced as lead solid or lead metal. So as the lead metal gets formed, it will precipitate to the bottom of the test tube, and the iron piece that we added into the solution will get oxidized to form Fe2 plus, and that is why the medium over here is turning a little bit of a yellowish green color as iron turns into Fe2 plus ions, and the solution above has started to change color, and the grayish precipitate that you see at the bottom is due to lead 2 plus aqueous ions turning into lead solid. So students, this is a very clear displacement reaction that has happened. So this would indicate that iron is found above lead in the reactivity series. And in the previous situation where copper 2 plus reacted with iron, this reaction indicated that iron is found above copper in the reactivity series. So iron is more reactive than copper and lead. The other solutions did not show a reaction, so we will observe that here. Magnesium 2 plus aqueous ion solution, does it show a reaction with iron? The answer would be no. There is no precipitate formed. The added metal pieces are still at the bottom of the test tube unreacted. This indicates that iron did not react with magnesium 2 plus aqueous ions. Why won't it react with magnesium 2 plus? Because magnesium is more reactive than iron. So in the reactivity series, magnesium will be found at a higher location or above iron. And finally, sodium 1 plus aqueous ion solution and metal reaction, you can very clearly observe that there has not been any reaction, no color change here, right? So students, that would indicate that between sodium aqueous ion solutions and iron metal, there is no reaction. This would indicate that sodium is found above iron in the reactivity series, or sodium is more reactive than iron. So students, we observed in this part of our experiment that iron or Fe solid is more reactive than mainly two elements, and those elements are lead and copper. Iron is more reactive than lead and copper. However, when it comes to all the other metal solutions, they did not show a reaction with iron solid. So this indicates iron is less reactive than sodium, iron is less reactive than magnesium, iron is less reactive than zinc, and when it comes to Fe2 plus ions, Fe2 plus ions will not get displaced by iron itself. So you can say out of the 5 other metals, after taking iron out of the picture, out of the 5 other metals that we have over here, iron is more reactive than copper and lead, but less reactive than sodium, magnesium, and zinc. So after noting these observations, we can now move on to the next reaction. Now students, let's move on to the final part of our experiment. In this part of our experiment, we are going to observe how zinc metal would react with different solutions we have over here. So we have few different solutions, and as we did in the previous parts of our experiment, we are going to take these solutions into these test tubes that are labeled. So we'll first take the first solution we have over here, zinc sulfate, and we'll add around 5 milliliters of zinc sulfate into the first test tube that is labeled zinc 2 plus. And then we have a freshly prepared ferrous sulfate solution over here, and we will add this ferrous sulfate solution into our Fe2 plus labeled test tube, or we can even call it the E2 test tube. And then to the E3 test tube, which is labeled Cu2 plus, we will add our copper sulfate solution. And to our E4 test tube, we will add our lead nitrate solution. And to E5, labeled magnesium 2 plus, we will add magnesium sulfate solution. And finally, to our E6 test tube, we will add our sodium sulfate solution. Now students, we have added the solutions into each of these test tubes. It is time for us to add the zinc metal to each of these test tubes. We have our zinc metal here. So we will take a small amount of zinc and add to each of these test tubes over here. Now students, we have added zinc metal to each of these solutions. We will mix each of these solutions really well. We do not observe a very fast reaction happening in any of these test tubes. For example, if you take our Fe2 plus or ferrous iron solution, you do not see any bubbling or any other reaction taking place really fast. But however, if you allow these test tubes and their solutions to come into contact with zinc metal for a period of time, at that point you will observe a reaction happening. For example, right now in the copper test tube, you can see a reaction taking place. As we mix it, you can see a brown color precipitate is formed already. So the reaction between zinc and copper is somewhat fast, but certain other metals is not going to be as fast. But in this case, if you take a look at lead and copper also, we can see, if you observe closely, around the zinc metal piece, we have some lead deposited on it. So this indicates that a displacement reaction has initiated. But when it comes to magnesium 2 plus and zinc, there is no reaction. Between magnesium and zinc, there is no reaction, students. And between sodium and zinc also, there is no reaction. Sodium 1 plus ions and zinc metal, we don't see reaction straight away. So we will allow all of these reactions to take place for a while, and then we'll come back and observe what solutions have reacted and what solutions have not reacted with zinc metal. Now students, we have allowed zinc metal to react with these aqueous solutions for a while, around 10 to 15 minutes. Now keep in mind, in the lab, if you do not observe a very clear observation within this given amount of time, you can first observe whether the metal surface is clean, and you can proceed to clean the metal surface and then proceed to do the same reactions again. And if the metal surface is also clean and still you don't observe reaction, to speed up the reaction, you may heat the solutions. But keep in mind, before heating the solution, if the metal surface is not clean, you will not obtain a reaction. So there are certain reactions that you should see. If you don't see those reactions, the reactions that should take place, if they are not happening, That is because you might have one of those problems that I mentioned earlier. Either the metal surface is not clean, or the reaction rate might be too slow. So at that point, you can speed up the reaction by heating the solution. Over here, what we have are solutions that are added with zinc metal. So let's take a look at the first solution. First solution is a solution where the zinc 2 plus aqueous ion solution was added with zinc metal. So students, over here we don't see any color change or any precipitate that is formed. So this is a very clear observation that zinc 2 plus will not get displaced in the presence of zinc metal. Zinc 2 plus is the positive ion of zinc metal. So therefore, zinc 2 plus will not get displaced with the aid of zinc metal. Then we move on to Fe2 plus or ferrous sulfate solution. And when added with zinc, you can very clearly observe there has been some reaction going on at the bottom of this test tube. You can see there are some precipitate particles that are accumulated at the bottom. So if you mix it well, you will see there is a slight color change, and the small solid particles that you observe over here are not very visible to the camera, but there are very tiny iron particles that are displaced by zinc. So zinc has shown a reaction between Fe2 plus aqueous ions and the zinc solid. So zinc solid will get oxidized to form zinc 2 plus ions, where Fe2 plus gets reduced to form Fe solid. So over here, students, iron solid particles are formed and they are dispersed around the medium, and the iron solid particles that are formed are quite small, and the amount of iron that is produced over here, since the reaction rate is quite low, you wouldn't necessarily observe a large amount of iron solid particles, but zinc definitely reacts with Fe2 plus aqueous ions and displaces Fe2 plus as iron solid. So that would mean zinc is more reactive than iron. Zinc is more reactive than iron, and zinc would be found above iron in the reactivity series. Then we move on to copper. The rate of reaction between copper 2 plus aqueous ions and zinc was quite fast. We observed after adding the zinc piece to copper 2 plus aqueous solution, after about 30 seconds itself, we observed a brown color precipitate getting formed. So you can see over here as well, a brown color precipitate is very clearly formed when zinc was added to copper 2 plus aqueous ion solution. So let's mix it and observe the color of the precipitate formed. You can very clearly see a brown color precipitate is observed. So this brown color precipitate is because the Cu2 plus, or in other words cupric ions present in the medium, got reduced to form copper solid. So zinc metal that we added to copper 2 plus aqueous ion solution was capable of reducing copper 2 plus or cupric ions to copper solid. So what does this mean? Zinc is more reactive than copper. Zinc is more reactive than copper. In the reactivity series, zinc will be found somewhere above copper. What about lead 2 plus aqueous ion solution? Zinc metal was capable of displacing lead 2 plus aqueous ions as lead solid. So lead 2 plus aqueous ions were displaced as solid lead metal in the presence of zinc metal. So zinc is more reactive than lead. If you mix it a little bit, you can see a gray color precipitate being formed here. So this precipitate is basically the lead metal that is displaced in the presence of zinc metal. So again, just to repeat what I just mentioned there. So the zinc metal gets oxidized to form zinc 2 plus, while the lead 2 plus aqueous ions get reduced to form lead solid. Now let's move on to magnesium. So in the magnesium 2 plus aqueous ion solution, do you observe a color change or a precipitate that is formed? No. In a magnesium 2 plus aqueous ion solution, when we add zinc, we do not observe any color change, or we do not observe any precipitate that is formed as well. So this would indicate that zinc did not displace magnesium 2 plus aqueous ions as magnesium solid. This means zinc is less reactive than magnesium. Magnesium is more reactive than zinc. Finally, students, our last test tube over here in this experiment, we have sodium 1 plus aqueous ion solution added with a zinc metal. Do you observe a color change over here? Do you observe a precipitate that is formed over here? The answer would be no. In the presence of zinc, sodium 1 plus aqueous ions do not get displaced. That means sodium is more reactive than zinc, or zinc is less reactive than sodium. That is why zinc metal was not able to displace sodium 1 plus ions as sodium solid. So now let's go over the reactivity of zinc over here. Out of the 5 solutions, 1 solution was zinc 2 plus, so we can disregard that because we know very well zinc metal cannot displace zinc 2 plus its own ions. So apart from that, there were 5 other solutions: sodium 1 plus, magnesium 2 plus, we have iron 2 plus, or ferrous ions that is, and lead 2 plus and copper 2 plus. So out of these 5 different ion solutions, we observed zinc was able to displace only a few. Out of these 5 different aqueous ion solutions, zinc was able to displace ferrous ions as iron solid, lead 2 plus ions as lead solid, and cupric ions or Cu2 plus ions as copper solid. So ferrous, copper and lead ions were displaced by zinc, indicating zinc is more reactive than all 3 of these metals. Iron, copper and lead, all 3 of these metals are less reactive than zinc. But sodium and magnesium metals are more reactive than zinc, so therefore you would not observe a reaction taking place when we add a piece of zinc into sodium 1 plus or magnesium 2 plus aqueous ions. Now students, with this, the main parts of our experiment are concluded. Let's go over the summary of our experiment. So initially we took copper and added copper to each of these solutions. We observed copper did not displace any of the metal ions in these solutions. Copper is the least reactive out of all of the metals that are present over here today. So copper was assigned the least reactive state, so we could find copper in lower ends of the reactivity series. Then out of all of the metals that we tested over here, magnesium was able to displace all of the metal ions as metal solids. However, magnesium was not able to displace sodium 1 plus aqueous ions as sodium solid. So this would indicate out of the metals that we added to these aqueous solutions, magnesium was the most reactive, but we had another solution over here, sodium 1 plus. Sodium 1 plus did not get displaced, meaning sodium was more reactive than magnesium. So the most reactive metal that we observed in this setup was sodium, because sodium 1 plus aqueous ions did not get displaced by any of the metals we added to it, indicating sodium was more reactive than any of the metals that we added to these solutions today. So sodium is the most reactive. Out of the metals that we have, sodium, magnesium, zinc, iron, lead, copper, sodium was the most reactive. Copper was the least reactive. So after sodium, which metal was most reactive? If you observe magnesium, magnesium reacted with the most amount of solutions over here, but magnesium couldn't displace sodium. 1 plus ions has sodium, that is why magnesium is less reactive than sodium. But magnesium was more reactive than all of the other solutions. Magnesium was able to displace copper, lead, iron, and zinc. So out of the solutions that we have over here, all of the solutions except for magnesium 2 plus itself and sodium 1 plus aqueous ions, magnesium was able to displace all of the other metals. So magnesium is the second most reactive element we saw in this experiment. Then we observed zinc. Zinc was able to displace 3 metals. So out of the entire set of metals over here, zinc was able to displace iron, lead, and copper. So zinc would be the third most reactive metal we have here in the lab today. I'm not talking about the entire reactivity series. Out of the metals and out of the iron solutions we have over here, out of the elements we were testing with, zinc is the most reactive out of the 6 elements we tested today. And then we have iron. Iron was able to displace mainly 2 ions. Pb2 plus ions got displaced as Pb solid, and Cu2 plus ions got displaced as Cu solid. Or lead 2 plus turned into lead metal, and copper 2 plus turned into copper metal in the presence of iron. So iron is more reactive than lead and copper, and since iron was able to displace 2 of the solutions as metals here today, iron will be coming on the 4th place in the reactivity of the elements that we have over here. So first sodium, then magnesium, then zinc, and then iron, and then we know copper comes in the last place. So we do know lead will come in the 5th place in the elements that we were considering today. So out of the elements that we were considering today, the most reactive was sodium, then magnesium, then zinc, then iron, and on the 5th place, lead would be the metal that is most reactive. So lead was only capable of displacing copper. We observed that earlier. So no other metal was getting displaced by lead. So lead is the 5th most reactive element out of the elements that we have over here, and the least reactive element out of the elements we have over here today is copper, because copper was not able to displace any of these metal ions as their metal. So students, that is all for the summary of this experiment. I hope by now you have developed a really good enough understanding about what we did here in the lab today.